I'm here to talk about Elasticsearch, or about search in general, how search works, what makes it fast, and as I know Elasticsearch best, I just try to explain it on the base of Elasticsearch. Before I start, any one of you already using Elasticsearch, Logstash or Kibana? Who's using Elasticsearch? Awesome. We can be short with introduction then. No. Anyone using Logstash? Great. So you can totally come to my next session after this one. Same for Kibana. And I want to talk today about a quick introduction about Elasticsearch, like what it is, what can it do. And then I just have a couple of examples like where I think speed makes a lot of sense for a search application. And I will also talk about the operating system and about aspects of distributed systems here. And what search actually means, what the notion of near real time is, which is basically quite a tricky term. I can just talk about myself. I joined Elasticsearch when it was named Elasticsearch 2 years ago. Recently got renamed. I work on Elasticsearch Core and on Shield, the security extension. And yeah, I'm interested in all things search and scale. And the company has been founded in 2012 and basically makes money with support subscriptions and public and private trainings. OK, so much for the marketing. Let's get started with Elasticsearch and search in general. So what is Elasticsearch? And this is an awesome description if you check out the website. Open source, distributed, blah, blah, blah. So it's lots of buzzwords in here, so maybe we should check each of those separately. And for me, the most important thing is that it's open source. It's Apache license, basically telling you you can totally build your own build and sell it if you want. That's a great thing about the Apache license. It's really free as in freedom. One of the important parts of Elasticsearch is that it's distributed and scalable, which basically means it can run on a single node on a single system, but you can also run on several nodes on several systems. So it scales up or out. So you can add in or improve performance by adding more nodes, or you can just buy the most expensive hardware you can find, which usually gets prohibitively expensive the more high-end the hardware is about to get. I think the interesting part is that it's highly available, and this basically means it can cope with failure. If a node goes down, you still want to have all of your data available, and you want the system to be kind of self-healing. So it tries to shuffle data around to get back to the original approach that all of your data is available twice in your cluster or whatever you have configured it, in order to make just sure that you can cope with those failures. And Elasticsearch tries to be smart and tries to automatically cope with failure to a certain degree, and we will see this covered later on. It's document-oriented. Which is also quite a tricky term. In terms of Elasticsearch, it means it's basically using JSON as its input and output format of getting data in, of requesting monitoring data or statistics. Everything is JSON. One of the reasons is that JSON together with HTTP is kind of the lingua franca of the internet. Every developer nowadays hopefully understands HTTP, and the same kind of applies to JSON. It's both the formats. If you don't get any of these things, neither HTTP nor JSON, you will have a very hard time developing applications today. And the next part is the actual part of the functionality of Elasticsearch, think of non-functional and functional requirements. Those are functional ones. And it basically means it's a full-text search engine, hence the name, obviously. And this means you query for terms like you do with Google, and you get back documents matching the terms based on some scoring formula. This is Wikipedia. Wikipedia switched a couple of months ago from their self-written 6-year-old Lucene engine to Elasticsearch. So every search on Wikipedia is basically using Elasticsearch, and full-text search is not just a document search. Like you know from Google, you get back website that hit, but it also contains highlighting in this example, like the term you typed should be bold. It also contains suggestions and highlighting in suggestions in this example. So full-text search is much more than just a simple term or a couple of terms matched against documents. And full-text search being much more is also analytics. And analytics basically means it's aggregations. So if you search something on Amazon, like a TV, you start by typing a term, but you usually drill down on your data by selecting facets on the left side, like I want to filter by a certain brand, or I want to filter by the size of the TV, something like that. And functionality like that is usually called facets or aggregation in information retrieval. And Elasticsearch basically uses aggregation. And the interesting part of aggregations, obviously, is you can draw it to make data more visual so that other people actually understand it who don't live in log files like most of the developers or administrators do. This is Kibana dashboard, which is basically the kind of visualization component on top of Elasticsearch. Again, if you're interested in that, just go to my next session. Spoiler alert. OK, how to get up and running with Elasticsearch, and that's one of the nice features. It's really easy. All you have to have is a JDK installed, and Java is ubiquitous nowadays, so you hopefully have that anyway. And you need to download the zip file of Elasticsearch. You need to unzip it, and just start it with bin Elasticsearch. And that's basically it. Wait a couple of seconds, and you have a fully functioning node, which allows you to index data, to query data, and your only requirement is Java 7. I think Java 6 is end of life, and Java 7 is supposed to be end of life soon, so Java 8 is fine as well. OK. By the way, if you have questions, just raise your hand and ask whatever you want to ask. I'm sure I forgot things. Let's talk about scaling. Scaling has a couple of different meanings. One part of scaling is actually your nodes, so that you have a cluster, and the other part of scaling is scaling your data. And they need to be seen from two different angles. The first one is the notion of what is a cluster actually. And when you fire up a single Elasticsearch node, this node basically pings around in its network and searches for kind of companion nodes. And if it doesn't find any, it just forms its own cluster. This is the reason why I can fire up a single instance on my notebook, and I will have a cluster immediately allowing me to index data. If another node already exists, and a new node is fired up, which you can also do in your notebook, you can just run bin Elasticsearch 4 times, and you will have a cluster comprised of 4 nodes. The next step is that this node pings around. It uses multicast for this. So it pings or it connects to a certain IP address, and all the other nodes basically answer, yeah, there is already a cluster. Do you want to join? And this means that after firing up a second node in a couple of seconds, you will basically have a fully functioning cluster. And this can be arbitrary in size. What this means is that a cluster is basically just the definition of several nodes working together, and no more, no less. Each node is its own process, so it can run on the same machine, it can run on another machine, it can totally run on a Docker container if you want, you name it. And one of the important parts here is that the number of nodes at the end of the day is an implementation detail. The user itself, using your cluster, should never ever care if it's actually a single node or 100. It just needs to access the service to execute a certain search, and that's it. And that's the whole idea behind a cluster. You can hide the number of nodes or whatever you have. OK, this is basically the basic notion of having nodes inside of a cluster, but this doesn't tell us anything about the distribution of the data. And this is basically the whole idea behind Elasticsearch compared to Lucene, which is a library which is used internally by Elasticsearch as well, that you can kind of scale out your data. And what you do is in this example that we use curl, command line HTTP client, and put a resource there. So we try to be RESTful, whatever this means. Everyone has a different definition of that. And we create a resource named A. And A is an index. So an index is just a collection of documents where you can put data into it. We basically, when creating an index, we decide into how many parts a single index should be split. And this is the unit of scale basically for your data. So what happens here is we define the number of shards to 4, and this means the index should divide it in 4 parts. And those 4 parts can be distributed somewhere in your cluster. So if you have 2 nodes, like in this example, and you have 4 shards, the data is kind of evenly distributed. Each node takes 2 shards. There's basically, inside of each cluster, there's one node taking decisions, which is called the master. The other nodes are only there to kind of accept those decisions. And when you create a new index, the master basically looks around, checks all of the existing shards, and decides where to put new data. So if you have one node that has a really full disk, new data won't be allocated on this node. If you have one node that already is either full of shards or has many shards, new data won't be allocated either. So there's just a couple of rule sets which are running through. And an important rule set, for example, is if you have copies of data, you don't want to put the original data and the copy of the data on the same node, because if this node crashes, your data is lost. And this is the next notion. So the weakness here with this model is if we lose one of those 4 nodes, we actually lose data. Not all of our data is available, so we don't have any safety. This means on top of the number of shards we need to configure for each index, we also need to configure the number of replicas, which basically allows you to configure how much copies of a shard I want to have inside of my cluster. And if you configure the number of replicas to 1, this basically means, OK, each shard should have a copy somewhere. So what happens next is that the master again decides where to put copies of this data. And the next step is basically that you put some replicas all across your cluster. And this means if you lose a node now, or you shut down a node because of maintenance, whatever, all of your data is still available, all index operations will still work, all search operations will still be able to access of your data. And this comes back to the high availability aspect. If one node shuts down, the master automatically tries to fulfill the promise of basically having 4 shards and 1 replica available. So it will start to rebalance data and shuffle data around in order to make sure it's completely available again after some time. Make sense so far? Any questions? Yeah, so the master basically curates a data structure which we call the cluster state. And the cluster state contains information which node holds which shards, and each node has a copy of this cluster state. So for example, when you execute a query, you don't have to care where the actual data is. Each node can just look it up and forward the query over there. And the master function here is that the master is the only node allowed to change the cluster state and propagate it to the other nodes. So that's the whole difference. Each node basically has a copy of the cluster state, always knows what's going on, but only the master is allowed to change that. And that's basically the reason why when you create a new index, only the master can decide where to put the shards, because he's the only one eligible to change the cluster state. OK, so let's talk about search maybe. The first thing we should talk about is like how to add data to an Elasticsearch cluster. What you can do is you can basically execute some sort of CRUD operations. So this is creating a resource. The HTTP verb is put. And you specify an index, a type, and an ID as part of the URI. So the index is books, the type is book, and the ID is 1. And the rest is basically the JSON body. So the body needs to be a valid JSON document, and this is going to be indexed. So in this example, we have Elasticsearch, the definitive guide, the book you should totally read if you want to get up and running with Elasticsearch. Has a relaxing 722 pages, so it's an easy evening read. And it has a publish date. And checking out the JSON, you can already see here that we can kind of infer data types out of the JSON. So name is a string. The authors is an array, but it's still string-based data. Pages is an integer. It would be really simple to infer Boolean data from JSON. And we try to be a bit smart with the date and figure out, OK, this is a date, so we should probably store it as a date instead of storing it as a string. This is important if you want to search based on the date or sort based on a date or have a range query, something like that. OK, what can I do? Obviously, after indexing data, you can get it back. So you just execute the GET request, and you basically get back the original JSON data along with the metadata being index, type, and ID. So it always allows you to see what kind of data you indexed. You can totally delete it. It's just one HTTP call away, so be careful with that, obviously. And the interesting part is that you can search for it. And this is basically the most simple approach of searching. It's like the Google type of search. You just underscore and execute search operation and specify a query. But the query is kind of a shotgun approach. We haven't specified any field. We haven't specified any range we want to filter on, like on date. It's just searching for Elasticsearch inside of your index, but you haven't specified anything. And we will get back to in a second how this actually works. Searches are usually more complex than just searching for a full text term, because you want to filter on data. You want to maybe execute a search based on typos, kind of a fuzzy search or whatever. So full text searches are really powerful, but this means you need to have some sort of expression language. And SQL is not the next best solution for full text searches, so it doesn't make a lot of sense to have a SQL interface. So Elasticsearch basically has something which is called the query DSL, and that allows you to really specify a lot of different query types. So if you take a look at this one, we have a query that, again, contains a filtered query, and the filtered query consists of a query and filter part. The query part is the full text search part, so you need to have some sort of scoring to decide how well a query, which is Elasticsearch in this case, actually matches a document. And this is where the whole full text search library with TF-IDF scoring comes into play. Whereas the filter in this example, which is a range filter and should just return documents which are newer than 1 year, is basically an in or out filter. So it doesn't do any scoring like a full text search does. The nice part about the query DSL, it's kind of extensible, so it's just some building blocks. And if you, for example, want to add aggregations and you want to count by category, so you execute a search for Elasticsearch for books newer than 1 year, but you want to know in which category, which is most likely IT in this example, how many books have been found, you will get another count in this example, and that's just the standard aggregation. Make sense so far? Already lost all? Question?
What do you get back from that search? Do you get back the search result in okay, what you get search result? Do you get JSON data back and some objects, or
yep.
do you get back the text query search?
So the question is, I need to repeat it for the microphone. The question is, what is actually being returned when we execute a search? First thing is, everything we return is JSON. That makes stuff very simple. What's being returned is basically some meta information, like how many shards we could successfully query. Imagine your cluster is in bad state and only a certain percentage of it is available. And then we start returning hits. So one thing which is being returned is how many documents matched your query. This may be 1 million, 1 billion, depending on what kind of query you executed. And on top of that, we return the first 10 results by default, which also contain the original JSON data that you indexed. We just return this so you don't have to query another data store to actually kind of reconstruct the data. And this is like from 0 to 10 by default, but it can be from 0 to 100, from 0 to 1,000, from 50 to 100, whatever you specify. Answers your question? OK. Yeah, and this brings us exactly to our next point. Oh, there's another question. Yeah. This is really working with a GET, but your question is rightfully, it also works with a POST. The problem is that many HTTP clients in many languages, including the Java default one, do not support a body on GET, even though it's completely allowed by the RFC. It is strictly spoken RESTful, a GET operation, because we don't issue any writes, but you can just use POST if you need to in order to make sure every HTTP client is supported. Yeah, the joys of HTTP clients. OK, so this goes kind of back to your question, how search is actually working and how it's executed. Because first, we are in a distributed system. You remember, the shards are kind of scattered around in your cluster, so search needs to be a bit smart in order to merge this stuff together. And what basically happens is that a search, if you search for books, like in the example before, we need to hit all of the 4 shards we created. And it doesn't matter if we hit a primary shard or a replica shard, a copy of that, because the data is supposed to be equivalent. So we just need to hit 4 shards, 4 different ones, obviously, and need to get the top 10 results per shard. So we kind of get 40 results. And from those 40 results, if we want to return the top 10, we need to list, or we need to sort this 40 results by score by default, which means how well the query matches our documents, but we may also change it for sorting by first name, whatever, and create a top 10 list. And this top 10 list then goes back to the shards and actually fetches the original JSON data which is being returned. But it wouldn't make a lot of sense to get back the 40 JSON data bodies and then sort them. So this is the reason why the search is basically kind of a 2-step process here. It saves resources. And only if we got back the original JSON data by default from the clients, from the shards, we can go back to the client and deliver the response. And this is one of the reasons, by the way, why Google doesn't allow you to page through page 10,000. Because going to page 10,000 with with 10 results each would mean we would need to get 100,000 results from each shard, sort this priority queue, go to result 100,000 to 100,010, and only return this to the client. And this is really expensive. No search application which is distributed will allow you to paginate. And this is the reason why. They need to have a 2-phase process, basically. OK, so what happens internally? We just saw Elasticsearch is handling searches on a per shard level, but maybe we should take a look at the shard itself. And the shard itself is basically just a Lucene index, so Elasticsearch doesn't have to do all the heavy lifting of full text searching. And an inverted index can be seen like this. So if we take the authors field, and we just saw there were 2 authors, Clinton Gormley and Zachary Tong, this is how the inverted index looks like for this document. So there's some sort of process chain going on, like lowercasing, splitting the term, like Clinton Gormley at its white space, and then putting it into this data structure. And this data structure is nothing else than an index in a book. You have a word or a term, and you have a matching ID, which is like not showing a page, but rather a document ID. Yeah, this is the sorted posting list. You can see this because the C is at the top, the Z is at the bottom, which basically means it allows us faster iteration. If we search for Zachary, we can kind of skip through this list and go to the end instead of starting at the beginning and being slow using a concurrent skip list. Okay, so we already talked about the JSON data being responded. And if you take another look at this data structure, we have no way of actually reconstructing the original JSON out of this one. We would be able to maybe reconstruct that it might be Clinton Tong, Zachary Gormley. It's really tricky. We can't like get back the original value because we also had some processing going on here. This is lowercase, but the original value was uppercase. So the data structure being stored doesn't look like the original JSON you actually sent to Elasticsearch. And in order to be able to return the original JSON, we just try to be lazy and take the JSON as it is and put it into its own field, which is called the underscore source field. This is just an additional field in the inverted index, which contains the original JSON, saving us a lot of hassle of trying to recreate it, because we just don't have to do it. This is just compressed and also stored in the Lucene index. The same basically applies to the all field. The first example I showed when searching was just executing a search operation for Elasticsearch, but we didn't specify any fields, we didn't specify anything, and we magically got back the original document. The reason for this is that Elasticsearch by default takes all of the values of a JSON document, no matter how nested it is, appends them in a single string, and takes this single string and puts it into its own field. And this field is called the underscore all field. This is basically the whole trick behind the query equals Elasticsearch. We don't query each field separately, because this would be slow as hell. We just take one field and query this one. And on index time, we simply take all the values of a JSON document and put it into their own field. Simple but efficient. Also, this obviously means that your index size might be considerably bigger using this all field by default. So if you disable it, you might save some space, but you can't do this kind of fancy shotgun approach querying for your data. Okay, there's a similarity or a similar function in Elasticsearch itself, basically allowing you to create own all fields or custom all fields, where you just specify, I want to take field 1 and I want to use field 2, combine them together, and just query a single field because it's faster than querying multiple fields and executing AND or OR operations on top of that. This functionality is basically called copy to, which just allows you to have your kind of all field inside of Elasticsearch, which is customized. So if I just want to search for the authors and the name of the book, I just create a custom copy to field, contain these two fields, and execute the search on top of that. Okay, let's go on. Why is search fast? This was just a couple of things. Another thing is that we use filters. We already saw filters being used in the example that only books which are newer than 1 year should be returned. And the trick with filters in Lucene is that this is a cached data structure. So if you execute the query and you filter by a category, we create a bit set. And a bit set for each document basically just contains a 0 or a 1 if it matches a certain category filter, like category for books, IT, whatever. And this bit set is cached and put in memory. And if another search, which may be a completely different query, but reusing the same filter is being executed, we can just check the bit set first and already exclude potentially millions of documents before we execute the scoring formula against it. Because scoring is computationally more expensive than including or excluding a document. And filters are one of the really neat functionalities which make search crazy fast. If you need to have in and out capabilities for filtering, always make sure you use filters in order to reuse this kind of cached data structures. Yeah, classic filters are basically a range filter where you want to filter for a certain price region or a date, for example, a term filter for the category, a geo filter if you just want to get results inside of a certain bounding box, if you have some Foursquare-like search, whatever. And because they're cached independently from the query, the probability of reuse may be very high. Obviously, if you know you never ever reuse your filters because they're kind of customized, you can disable caching them. Question?
Where are the filters stored? Are they per node or per cluster?
They are stored per node in the heap. So if you, I mean, it doesn't make a lot of sense if you have like 5 nodes and one of them doesn't hold any data. It doesn't make a lot of sense to put the filter cache there, and we want to avoid round trips. If you would need to go to another node asking him if something is cached, the probability of reading this whole file on disk with an SSD is higher until we get the response. So they are always on node level. And the main reason is because it's part of Lucene, so it's part of a shard, and a shard always belongs to a node. Okay. Another interesting feature is something we call the exists and missing filter, which basically allows you to execute a search to search for documents that don't have a certain field. And usually when we index data and put it into the inverted index, we have the inverted index, which is like the field name, and that contains data. But if the document doesn't have any field, it's usually really hard to find out because it's not mentioned in the data structure. And the naive solution is you just like kind of parse every single posting list and search if the document is inside of this or not. So you create a set over the documents, and then you know if this document is in or not. And this is crazy expensive. And it doesn't scale. So the higher the cardinality of your fields is, so if you have many different values, the longer your posting list is and the slower this whole process gets. The solution for this is that you just take all of the field names of a JSON document and put it into their own field. And this is called underscore field names. And now you can cheaply query this single field, and because it's a full text query, it's crazy fast. So the exist and missing filter like got sped up with a factor of 50 or 100 with this tiny optimization. Questions before we go on to aggregations? Question there.
You said the index is lowercase. Do you have characters outside of the ASCII range in your index?
So the question was, I say the index was lowercase, and if it's possible to store non-ASCII stuff in there. First, Lucene is completely UTF-8, which allows you to basically store anything. Second, this was just an example of how an analysis chain could have been executed. So it's not, if you have like Japanese characters, you have a problem to split them because there's no space character inside, and you need different notions, and there are different analyzers, as they are called in Lucene, which allows you to kind of split this data, to post-process it, because you can't really lowercase Japanese characters either. It doesn't only make sense for Western characters. And it highly depends on the language and on how you configure how data is stored in the inverted index. And the lowercasing was just one example, which Elasticsearch is doing by default. There's something called a standard analyzer, and that one is basically lowercasing, splitting not only at spaces, but there's also a UTF definition where splitting occurs, like after a comma, for example, because you don't want to put the term with a comma in the inverted index, so you need to remove the comma, the dash, exclamation marks, and so forth. And that's basically the process of analysis in Lucene. And that one is highly, highly configurable. OK. Let's go on with aggregations. Aggregations is kind of, executing counts on top of documents that match your query. And aggregations basically consist of buckets and metrics. If we go back to the aggregation where we aggregate by category in our book search, and we have a category for like novels, maybe more fine-grained instead of just novels. We have IT, we have cars, you name it. And this means the documents kind of fall into those buckets depending on the data. But if you have those buckets, you usually want to do something with it. So the simplest metric, which you can do on top of those buckets, is basically counting them. So how many documents fall into this bucket? But if you have numbers in there, like a shopping revenue or a shopping cart size or something like that, you may want to find out your average revenue, your maximum revenue, your minimum revenue. So you can execute all kinds of fancy things with the documents being in these buckets. And that's the whole idea of aggregations. And one of the nice features is you can like nest arbitrarily deeply. So you can first maybe group by day if you have an orders index, and then like find out the average value of your shopping cart for every hour, but this group by day or whatever. So you can go arbitrarily deep. This goes like into, I don't know, what's it called, analytics, business intelligence, whatever you have. And the nice part about Elasticsearch is like you don't need to create another schema to your like kind of star database or what you name it, but you just can add more aggregations and do this on query time. And the problem with aggregations actually is that you cannot really use the inverted index for this. And the reason is that instead of mapping the term to a document ID, which we saw in the inverted index, we need to map a document ID back to its terms. Because we execute the query, we know what documents are part of this query, we know the document IDs, but then we need to take all of those document IDs and see into which buckets we fall. So we have to uninvert this index, what's it called. And this is what Fielddata, the data structure used for aggregations, basically is doing. And if you take another look here, this is our inverted index, the one which is stored when we index data. And the Fielddata below is the data structure we need for the bucket calculations to put the document ID in. And again, we cannot reconstruct the Fielddata out of this data structure. It's Clinton, it's Gormley, we don't know which is the right position, we don't know the original value. So instead of just writing the inverted index data structure once, we can write it 2 times and just write it in a different manner the second time. And this one is basically the raw form, which takes the original value, like Clinton, Gormley, and Zachary Tong, and writes it through the inverted index in addition to the existing one. And we can use this one for aggregations, because it's really easy to create the Fielddata data structure from the data structure above. And we can use the other one for executing searches. And that's the whole idea for aggregations. We need to store it in a special format in order to start being able to use it for the buckets inside of aggregations. Make sense? Question?
Fielddata stuff is an extension. It's not in Lucene, right? That's
yeah.
Elasticsearch.
There is a Fielddata structure in Lucene, but we never used that because it was kind of limited, and we also use this data structure to load geopoints in memory and execute calculations for distances, for example, and that never really worked with the old thing. I'm not sure if it's still there in Lucene 5. And yeah, the biggest weakness of this, before we go on, question? Can you?
What a bucket is?
So the question is, what's a bucket? And a bucket is maybe basically just a list or a map where the documents which fall, for example, into a certain category, like IT in my example. So if you aggregate by category for the books example, you will have books that fall into the IT bucket, you will have books that fall into the novel bucket, and the documents are just kind of flowing in there. And if the query is finished, we just go into this bucket and execute a metric on top of that, like the number of documents or the average value of the shopping cart size, you name it. Kind of, yeah. But it can go arbitrarily deep. You can have buckets inside of buckets inside of buckets. And this is where it gets fun in terms of analytics. OK, one of the disadvantages of Fielddata is that we kind of lazily construct it. So when you execute the query for the first time, we create this in-memory data structure and work on that. One of the reasons that we create an in-memory data structure is for every document which is inside of this bucket, we don't want to go to disk and extract the value because this would be crazy slow. In order to speed this up, we just take all of the values from disk and put it into memory and then execute the aggregation. And this is the lazily construction, creating this in-memory data structure. And the other problem, it's easy to go out of memory with this. If your data set is actually bigger than your heap, the amount of memory you basically configured for the Java process, we either go out of memory or we have protections for this in new Elasticsearch releases, which is called a circuit breaker, which basically aborts the request in order to keep the service alive. So it kind of counts memory while Fielddata is loaded, and if it finds out, this is maybe too much and I don't have that much space in my heap, it just aborts the request for stability. Nice feature in terms of stability, but you still don't get your query back, so this is only partially successful. So the other feature which we recently added is something we call doc values. It's again a Lucene feature. And instead of loading the field data structure lazily on query time, we create it on index time and write it to disk. The main advantage of this is that we never ever have to put it in the heap, so we prevent out of memory. It's just in the file system cache of the operating system. And that's a nifty trick to kind of prevent those out-of-memory exceptions. We can like lower the heap by gigabytes if you use doc values and load stuff from disk. And that's going to be default in Elasticsearch 2.0. There's a question.
Are doc values something like memory maps file?
It's part of the Lucene index, and that one is memory mapped. Okay. Yeah. So basically, you can configure Lucene to memory map parts or not. And Elasticsearch tries to do the smartest thing for you. But you can memory map files there because it's usually the simple solution to load data into the file system cache as well.
You said newer versions have the circuit breaker. Since when it is in?
So the infrastructure, I think, has been there since 1.2. But our idea with the circuit breaker is to extend it for far more things. So we started with field data because this was the #1 problem people ran into. But we want to extend it so you can do deep pagination, for example, because deep pagination also can run you out of memory. And we want to extend it for every request where you can like do bad things. We basically just want to protect the user and make sure each node stays up. But it's not there where we want to go. We basically created the infrastructure now and applied it to field data. It's also enabled by default, by the way. And if you change sizes of your heap, like how much memory you want to have for field data or for filters, you can configure this. Make sure you adapt this value as well. I see you taking notes. That's good. OK, let's go on with aggregations. Another question.
Regarding doc values, so what's the drawback of doc values? A bit slower? Or?
It's a bit slower. And more disk space, and you have to make sure you run warmer APIs to make sure that this part is in the file system cache. Otherwise, we have really to go on disk. But Lucene heavily relies on the file system cache. So you need to have enough main memory and have less heap, and then it shouldn't be a problem. But it might still be a bit slower.
What was the question again?
So,
please repeat that.
yeah, I forgot. What was the question again?
What's the drawback of doc values?
Yeah, so the question was, what's the drawback of doc values? And storing stuff on disk usually requires you load it first, and so we need to put it into the operating system cache. OK, a couple of interesting aggregations we have, because it's just a reuse of existing probabilistic data structures. The first one is the counting of distinct elements. The naive solution is you just create a huge hash set, put every value in it, and then measure its size. This might work, but it doesn't work in a distributed system because the hash set values might be different, so you can't just merge the sizes. It means there would be one node which gets all of the values, and this is a crazy idea for distributed systems. So the solution here is something called the cardinality aggregation, which uses a probabilistic data structure called hyperloglog++. There's a paper on hyperloglog, and hyperloglog++ I think is just the extension that it's absolutely accurate on low values, on low cardinalities, because hyperloglog I think has a skew in there if I get it right. The interesting part here is that you basically can, it's not 100% exact, but you kind of can trade in memory for exactness. And I think this is a smart solution. If you know how many memory you have, if you're willing, how much space you actually want to invest into a single request, you can just change the accuracy. And yeah, at some point in time, it has a fixed memory usage completely independent from your number of documents. So if you're once set with some configuration, you're fine with that, you can just go ahead. Another interesting thing is the percentile aggregation. Again, the naive implementation of percentiles is that you need to have every value in memory and then like find out where the 99th percentile is. That's not really fast or scalable because it doesn't really scale with the amount of documents coming in. There's a neat algorithm called tdigest, which is based on another algorithm called qdigest. I think it's been written by Ted Dunning, the Java library. And the nice part here is if it's a small set, it's 100% accurate. If it's a big set, again, I think you can you can configure the accuracy. And the third interesting part is that the more extreme your percentiles are, the more accurate this algorithm gets. So if you use the 50th percentile, that one might have a stronger offset with the real number of percentile or cardinality there. But if you go to the 99th percentile or 0.9 or whatever 0.9s you have to fulfill your SLA, this one gets more exact. And yeah, I mean, if you get the 50th percentile, I think you can just use a median anyway, so that doesn't need to be exact. All right, questions? Great. Let's move on. Operating system and hardware. So a couple of things to keep in mind here. The nice part about Elasticsearch is it can absolutely max out any of your resources and render your system unusable. That's awesome. So you kind of have to decide what's the most important service and how you want to prioritize things. So the main idea here is basically that the CPU can waste a lot of resources on indexing and searching, which is not really waste because this is what Elasticsearch has been built for. You may need a lot of memory for aggregations if you don't use doc values. You need I/O for indexing and searching, like constantly creating those inverted index. Obviously, it takes a lot of time when indexing documents and takes a lot of CPU. We might need good network connections, because if one node falls over and we shuffle data around, you can like easily shuffle half a terabyte of data around in your local network, so make sure it's fast. So the basic idea behind this is to kind of throttle data. If you know that you want to make sure that searching is always working, and it's not so important that writing is always at writing at maximum speed. When indexing data, you can kind of throttling the writes of data to like a number of megabytes per second and make sure that your search is still up and running while your system has load due to indexing. And you need to kind of decide about trade-offs, what's useful, what's less useful when configuring Elasticsearch. So in my opinion, the most important part is always that you're able to search. But imagine you have some kind of search logging cluster going on. Then it's always really, really important to write the data, and maybe you can live with some slower searches actually, because if you wait 1 second or 2 seconds for log files, might be completely fine. Yeah, it's what we basically do in Elasticsearch. For CPU, we kind of scale the thread pools we have inside of Elasticsearch based on the number of cores. For disk, it's easy. Just use SSDs, and you can mitigate a lot of performance issues. Memory can just be simply unlimited. So you have a lot of money, just buy more memory. The reason is you shouldn't just waste everything of it for the heap, but you can just use it by the file system cache. So if you don't use memory, the operating system will claim it by itself and use it for loading data. You all know this when you cat a file on your notebook. The first one maybe takes a second, but if you cat a file the second time, it's there instantly. The reason for this is the operating system put the file in the file system cache, so it's in memory. So for the operating system at this point in time, it's just an in-memory operation. And Lucene makes heavily use of this functionality of the operating system. Yeah, network, the faster the better. Simple formula here. I already talked about the file system cache. Make sure you don't thrash the file system cache all the time. So don't run a second service like a SQL database so they compete for those resources, because this means that suddenly Elasticsearch gets kind of unpredictable in terms of query performance. We have people telling us that at 6 a.m. in the morning, Elasticsearch is dead slow. Main reason for this is usually Unix or Linux systems have a job running which updates the locate database, which is used by the command line locate utility to find files. And they go through every single file and check its contents. And this means your file system cache gets completely thrown away. Don't do this. Like, make sure your system keeps fast and keeps this stuff in the file system cache. There's another feature which is called memory locking in at least Linux systems. I think Windows doesn't have it, but we all don't run Windows, right? Right. So memory locking basically allows you to tell the operating system to never ever swap out this single process. And that's really important, because if you swap out something, it gets swapped out to disk usually. And if you do a garbage collection and part of your memory is on disk, you can just grab a coffee, but you should never ever hope that you get a near real-time contract for executing searches. So this is a really, really, really important setting. If you don't swap in general, maybe it also makes sense to not create swap files at all. If the system goes out of memory and hangs, at least it's gone. Then it means it's not slow. Might be a good thing. There are still people configuring the out-of-memory killer in Linux systems, which is a smart way of, oh, look, there's not enough memory. I'm going to kill arbitrary processes. And the kernel is doing this. The problem is the kernel usually kills the process needing the most memory first, which in most cases is Elasticsearch in your system if you have it up and running. There's a question.
No question. I think you can also add some sort of priority to your processes, so you can steer the OOM killer somehow. I've read about this.
Yeah, just disable it. Okay. Don't pray that the OOM killer will cope with priorities.
So basically, if you disable this one, then the system will lock up. That's what you said. So
yes.
You can't kill
it will not try to free memory by killing processes. I think it's a bad idea just randomly killing processes, and this is what the OOM killer does.
But what happens then? Because it is not enough memory, right? And something has to happen.
I think if you run into a kernel OOM, you badly misconfigured your system. So the OOM I was talking about before was a heap OOM of the JVM.
Okay.
And that's two very different things. If you hit a kernel OOM, you're in deep, deep trouble. And this means you may have configured the heap to take more space than you have memory available. And you should never do that. Or you have many different processes like Elasticsearch, a SQL database, something that needs a lot of memory for calculating whatever you need, and then suddenly the VM decides to like kill things.
So just to recap, this ORM killer that I see there is some Java internal.
No, this ORM killer here is from the operating system, and you can disable it by setting it in the or by setting a 0 in the proc file system. The other one, the out-of-memory exception that happens in the JVM, there's simply nothing you can do about it. If you hit it, you have a problem because the JVM behavior after an OOM is undefined. Your service might go on, it might continue and be able to serve requests, but maybe it write the data corrupted. And that's a problem because the most simple thing would be to just shut the JVM down, but that doesn't happen. Okay, one last point about distributed aspects. I think this might be known. It's like known as the fallacies of distributed computing, aka like how a network can screw up. And the point here is, I was talking a lot about speed and how we speed up things in Elasticsearch. In my opinion, like distributed systems are a bit different here because the distributed aspect adds a lot of unreliability here. And the most important part is like to get reliability and stability first before we can cater for speed in distributed systems, like with communication going on. And these things happen. Like people ask, why is my query slow? Maybe it's a garbage collection. Maybe your network is screwed up. Maybe your switch has a loop routing in its topology configuration. Like there are so many additional things you can run into. Like bandwidth is never ever infinite. We need to, like when we shuffle around gigabytes of data, you may have an impact in your search application. Transport cost is 0. There is no 0 latency when sending data from A to B. It won't happen. And it's hard to debug, and it's even harder to like measure. It's part of your performance benchmarks. And don't run a performance benchmark on your single node laptop and then think the values are the same for a 10 node cluster. It won't happen. Make sure you keep this in mind. Okay, quick wrap up. First, we do a lot of stuff in Elasticsearch like to keep things fast. Well, this doesn't mean we can't like improve things, and we will continuously improve things. And the second step, or the second point is, I think one of the most important points of search applications. At the end of the day, search is a trade-off. Like either you decide to do things at index time and maybe a little bit more slow at indexing, but you may need more disk space, you may need disk space is one of them. But the point here is, so you may need to like change the format of your data before you actually index it, so you have some work upfront. But then suddenly stuff is blazing fast when doing it at query time. Or you are lazy and you do stuff at query time and you're willing to bite the bullet of, for example, more memory consumption, like in the Fielddata example, where there's a parent-child functionality in Elasticsearch which takes more memory. And search is basically a trade-off like this. And just keep this in mind when like kind of designing your applications. If your search is slow, maybe there's a possibility you can like just offload things to the index time and make sure it's fast on query time. Yeah, I linked to the benchmarks, but I think the more important point here is if you do benchmarks, please do your own. The internet is full of benchmarks, and the internet is not full of awesome benchmarks, and especially the internet is not full of your benchmarks with your data. So if you want to get reliable numbers, benchmark your own numbers and do it yourself. We have a couple of minutes left, so I can waste them talking about the next Elasticsearch release and what's going to be about speed there. One interesting part is that instead of you having to configure throttling manually, we try to be smart and kind of throttle ourselves. So one functionality is to find out if you run on an SSD or not, and based on this information, we can decide if we are lagging behind with merges or with index operations, and throttle those operations. So we kind of create back pressure on our way instead of just trying to keep indexing data and then hoping everything works out, or instead of just having a hard cap at 20 or 50 megabytes per second, when in reality we could sustain a much higher load because the other operations which usually run in the background just don't occur right now. The cluster state I've been talking about is right now a really big data structure, and it's continuously being updated and sent as a whole to the other nodes. And an easy optimization is to just send diffs, so we actually don't have to send the whole data structure around, because that one can easily be like 50, 60, 70 megabytes. And this just saves a lot of bandwidth, and updates are going to be far faster. Recovery is one of the biggest pain points for Elasticsearch users in production, because if you restart your whole cluster, it suddenly takes a lot of time until it's ready again, because it has to kind of parse or check the integrity of all of the data. And we just add a feature called index sealing. It's going to be part in the 1.6 release even, which allows you to like mark an index as read-only. So immediately on startup, we know, OK, this has not been written into. I can just fire up the index as it is. And this will make cluster restarts kind of instant. Aggregations will get another feature or more features. So right now with aggregations, you can like kind of have this multi-dimensional queries. But the next level of aggregations is that you can create aggregations based on the values of the aggregation results. The common example is moving averages. You just want to know a value over time in like, I don't know, an hour period or stuff like that. And this will be possible with the next generation. Queries and filters are going to be merged. So you just have to specify one of them. You saw the query at the beginning where we specified query and a filter. But if we filter by a date, like just show me all books from the last year, it's kind of implicit that this is an in and out filter. So we don't have the user to specify it. We can be smart ourselves. There's a reindex API, which makes it easy to like reindex data from one to the other index. There's a changes API, which basically allows you to do some kind of data center replication over time. But this requires Lucene changes and the scripting engine. And yeah, I can later talk about Lucene stuff, but we have a query first.
So in Elasticsearch 2.0, there will be breaking changes in the API, I guess, right?
Totally. That's why we do major releases, to break stuff. So the question was if there are breaking changes in major releases. And we did the same in 1.0. We tried to be stable from 1x to 2x all the way up. We're now at 1.6, so we still have 4 minor releases left until we have to break stuff. And yeah, for every major release, we usually like accumulate changes and then do breaking stuff. But I think from this stuff, there's nothing which should be really breaking. It's more like query types which we deprecate. We will remove lots of stuff in the mapping because the way we handle types is not really smart. So there will be breaking stuff. And the most important part is if you upgrade to Elasticsearch 2.0, which comes with Lucene 5, it means that indices with Lucene 3 cannot be read anymore, so with really old, which is a problem when you have time-based data. And we often upgrade API already in existing Elasticsearch versions, which has to run to like recreate all of the data structures internally to make sure they are still be read when updating. OK. Yeah, I can talk about Lucene, but we only have like 4 minutes left. So Lucene is like constantly improving and evolving over time, which is pretty amazing because it's a 10-year-old library, but they still find speed improvements with like 10x factor, which is pretty crazy. The most interesting part is the bitset compression, actually. I was just talking about filters, and they didn't ever compress bitsets. So if you have like 2 million values, you needed 2 million bits. But it's just zeros and one, and we usually learned with compression that you can kind of compress numbers, like ranging from delta encoding or whatever. And there's something called a sparse bitset, which had like a 2x compression on the data. But there's something called a roaring bitset. I think it's on roaringbitmaps.org, the whole principle, which basically divides all of the bitsets into smaller numbers and just stores those smaller numbers. And that one has a 50x size compression based on normal bitsets. And because they are so small, it's also 4 times faster. And those are the new defaults in the next Lucene release, which is pretty nice. Also, the SSD detection, the adaptive merge threading, all of this is basically part of Lucene, and we can just easily utilize it in Elasticsearch. We do a lot for index safety, so to prevent data corruption, which also needs to be put into Lucene and should not be part of Elasticsearch because it is the core. And this is also constantly going on. There's also index compression improvements. So with the Wikipedia data, which is kind of the nightly benchmark data for Lucene, they get like also a 2x improvement compressing the data. It's pretty neat what they're still able to improve there. OK, so I'm pretty much done. Do we have questions? Is it a question, or you were just like yawning? OK.
Do you think that Elasticsearch could be faster if it was written in C or C++, for instance?
So do I think if Elasticsearch could be faster if it was written in C or C++? I think it could be faster if it was written in assembler. The point is that there have been so many menus also put into Lucene. that the foundation you would have to build Elasticsearch would have been so much more years or decades of work that, in my opinion, it's not worth it if you can easily scale out. The time of engineering, especially put into Lucene, is so crazy that rewriting this stuff with the like proven testing ideas behind Lucene would take you ages to decades, and I don't think it's worth the trouble.
Is Lucene made by Elastic, or is it something made by
No.
the community?
So the question is Lucene made by Elastic or by the community? Lucene is an Apache project since 10 years, and it's a complete community project. We just happen to have a lot of committers which also work on Elasticsearch and Lucene, but Lucene is not controlled in any way by Elasticsearch because it's an Apache project. Question?
So I go just to check. So currently Elasticsearch is the second most popular search engine at the moment. Solar is the, now this is according to Wikipedia. I'm looking at you, I'm sure you don't know. But
Possible?
what's the difference, roughly?
Between, so your question is what's the difference between Solar and Elasticsearch?
Yeah, and there's another one that's longest one, I don't know.
Yeah, that's, we can leave that one out. So the first thing is,
Both based on Lucene, right?
both are based on Lucene actually, Solar as well as Elasticsearch. And like Elasticsearch is not that old. Solar is also like 8-9 years old. So Elasticsearch had kind of a fresh start in terms of code, in terms of libraries being used. The idea behind Elasticsearch was to be distributed from the start, and in Solar it was kind of an afterthought. The query language is a bit different, but the core is the same. So at the end of the day, you need to find out what kind of functionalities you need. Both have different strengths and weaknesses, and the important part is you check it with your requirement. I mean, obviously, if you ask me what's better, I'm kind of biased here. So my opinion about that is you have to try it out. Last question, because we are over time. Question is if Solar also does have this aggregation stuff. Solar has faceting, which is a one-dimensional aggregation, and I think they're going to add something similar, which is also called aggregation. But it's, yeah, I mean, the feature sets of those two are like sometimes merging, evolving. The important part is that this works in a distributed manner, and then it still works, and this is what we are trying to get right primarily. All right, I think we're done. It's 12. Thanks.